Okay, let's go through the today's lecture and let's see if we can figure something out for this game as well. Okay, so we are here on all pairs shortest path. और हमने यहाँ पे so our input is in adjacency matrix. Okay, adjacency matrix is a matrix which represents a graph. It has a 1 wherever there is an edge, and it has a 0 where there is no edge. Last time I created a sort of a pseudo adjacency matrix from adjacency matrix, which looks like this. Which looks like this. So we have weights wherever there are weights on the edges, and we have 0 along the diagonal, and we have infinity where there is no edge. And I later on said, okay, this matrix, do this, that this matrix is actually a distance matrix, which does not use any of the vertices. So this is a distance matrix which has only single edge paths. Okay, there is no path of length more than one edge. Okay, we don't use any more than one edges. So if we don't use more than one edge, then the distance between a vertex A and a vertex D here is infinite. Okay, you can't go from A to, so I'm talking about this thing, right? Since अगर इस तरह का edge नहीं है, तो I can't go from A to D, which means that the distance from A to D should be infinite. Okay. But I can go from A to C, which means that इसका जो distance है वो इस edge का weight है, which is 9. So that's it. This is the pseudo adjacency matrix, which represents the distance between two vertices if they have an edge between them. Otherwise, it does not. Okay. And the distance from a vertex to itself is 0 by definition, जैसा हमारे पास पहले था. So far so good. फिर हमने कहा था कि we can extend this definition to use more than 0 intermediary or auxiliary vertices. Okay, so this is ये जो हमारे पास pseudo adjacency matrix है, it does not use any auxiliary vertices. Okay, it does not use any vertices on the path from the vertex I to vertex J. Okay, it only uses vertices I and vertices J. So now I said, okay, let's move on from here. Okay, let's go and use more vertices to create a path from vertex I to vertex J. To do that, we first order the vertices from, let's say, 1, 2, 3, 4, 5 up till n. Okay, so let's name the vertices 1, 2, 3, 4 up till n. तो हमारा जो pseudo adjacency matrix है, that's just A of ij 0. Okay, it's the distance matrix that only uses the vertices I and j. I and j, 1 would be the vertex. 1 would be the distance matrix that gives you the distance from the vertex I to vertex j, but it is allowed to use vertex 1. Okay, it is now allowed to use this one vertex 1. Okay, and let's see how it changes our adjacency, this distance matrix. Okay, so let's actually no, let's क्या so उसके बाद मैंने ये कहा था, I'm just trying to summarize what we did. उसके बाद मैंने ये कहा था कि हमारा जो goal है, the thing that we are looking for is the distance between every pair of vertices, and it does not care कि वो जो path है, shortest path, वो कितनी vertices से गुजरा है. It is allowed to use all possible vertices in the graph, which means जो distance matrix मैं ढूंढना चाह रहा हूँ, मेरा जो goal है, that's actually aijn. Okay, this is my goal. I'm looking for n, where ij is the distance from ij, but it's allowed to use all n vertices. Okay. So to create a sort of optimal substructure, I must be able to compute this matrix from some previously computed matrices. Okay, so my sub problems are going to be these aij's for smaller values of this index, okay, which is the number of vertices I'm allowed to use, or the set of vertices that I'm allowed to use, and I'm going to recursively compute this using smaller instances, smaller solutions. Okay, so my goal is to, for example, compute a k of ij using values of so I'm using values of a k minus 1. ओके, तो इस तरह की अगर मेरे पास पहले से कोई मैट्रिक्स कंप्यूट हुई हुई है which uses only k minus first k minus 1 vertices, so I should be able to somehow find a function which I can use to compute the values of matrix which uses now one extra vertex. Okay, if I can do that, so I would be in good business, right? Because now this is what I want. I can to compute this, I'm going to have to compute a n minus 1. Then to compute this, I'm going to compute a n minus 2, and so on, right? And a0 तो मेरे पास पहले से a0 is this matrix जिसको मैं pseudo adjacency matrix कह रहा था. Okay, this we realized it's easy to compute. In this matrix, all I need to do is keep the diagonal entries 0 and all other entries make them infinite. Okay, this is a0. So now goal is to find to go from a0 to a1, from a1 to a2, and so on. Okay, that's my goal. If I can do it, so I'm good, right? That's it. That's my solution. Then I can probably memoize on these a's, and then do the usual dynamic programming. Do we have any questions so far?
No, sir.
Okay, all right. Good. So our goal now is to figure out how to go from a k minus 1 to a k. Okay, how do I actually, if I know the shortest path from I to j, which uses only first k minus 1 vertices, how do I compute shortest path or the distance from the vertex I to vertex j using first k vertices? All right. Okay, let's see how do we do it. Okay, so let's say let's say this is my vertex I, this is my vertex j in my graph. Okay, there are probably, I don't know, edges here or not, I don't care. Let's say there's an edge, iska kuch weight hai, wij, and let's say this is the set of vertices v1, v2 up till vk minus 1. Okay, और मेरे पास ये जो एंट्री है a k minus 1 ij, this gives me a shortest path which uses which may use any of these vertices. It's not necessarily it must use each of these vertices. Maybe not. Maybe this edge is actually the shortest distance from I to j, right? But it is allowed to go through any of these vertices. Okay, but it's not allowed to go through the remaining vertices. Okay, let's say these are the vertices, remaining vertices. Okay, but there is this new vertex vk जो अब मैं allow करने जा रहा हूँ. इससे पहले this was not allowed. Okay, do you guys see the picture? So I have these two vertices I and j, and I want to find out their shortest. I actually want to find out their distance, which may use any of these vertices, which is now allowed to use these vertices, and which must not use any of these vertices. These are not allowed, these are already allowed, and these are allowed now. Okay. All right. Now the question is, if I know the shortest distance, so distance is always shortest. I'm looking for the distance which uses these k vertices now, but I already have the distance which uses these k minus 1 vertices. Okay. Um, any idea how I can figure it out? So remember, ये जो मेरे पास a k minus 1 है ना, this a k minus 1 is a matrix which contains distance for every I n j. मेरे पास हर पेयर का वर्टेक्स का इसमें डिस्टेंस है, which only uses k minus 1 vertices. K minus 1 auxiliary vertices. Okay, so it's possible कि ये जो I and J है, ये I is probably the, I don't know, first vertex, J is the last vertex, J is probably Vn. Okay, so ये खुद इस सेट से बाहर हो सकते हैं. Okay, I and J need not be in this set. Okay, they are allowed to be outside the set. But इस path के ऊपर और जितनी vertices हैं, इन दो के अलावा, they all must be from this set V1 to Vk minus 1. Okay. Good. So now our goal is to find out how do we actually find a shortest path which only uses V1 through Vk, using the shortest distance, shortest path which only uses V1 to Vk minus 1. So the thing is, you can do this by something that we learned the last time we were doing single source shortest path. The last time we did single source shortest path, we actually used something called triangle inequality, which says that the distance between three vertices, if I have three vertices A, B, and C, so this is B and this is C, okay? The distance between A to C is always going to be less than or equal to, ये हमने कहा था कि this quantity, let me call this X, Y, and Z, and we said that X is always going to be less than or equal to Y plus Z, okay? This is the triangle, the famous triangle inequality. Which means, so let's forget about this, okay? ये वाला तो हमारे पास edges allowed नहीं है, okay? So this is my allowed graph. इस allowed graph में I want to find out, I want to find out a shortest path from I to J, okay? There are two options. एक option तो ये है कि इस graph में, so again, इस discussion के लिए I am assuming कि ये वाली vertices तो exist ही नहीं करती, right? We don't care about them at this point. So to compute the distance from I to J, I said there are two options. एक option तो ये है कि we actually don't use this vertex Vk. The shortest path actually does not go through Vk. If it does not go through Vk, तो फिर A of k ij is actually A of k minus 1 ij, right? अगर k इस vertex में से shortest path नहीं जाता, तो वो shortest path यहीं पे कहीं से जा रहा है ना, जो हम पहले से compute कर चुके हैं, right? So that case is already उसका हमारे पास solution है. The distance between I and J, अगर उसका shortest path k से नहीं जाता, तो फिर we already have the solution. We already know that this thing is actually what we were looking for. Okay, so this is one option. Okay, अगर shortest path k से नहीं जाता, this is going to be our distance. And the second option is कि shortest path actually k से जाता है. Okay, which means कि इन्हीं vertices में से कोई एक path होगा which goes to k. Okay, and then let me use red to show you the other end. And then there is some other path which goes through some of these vertices and then goes to J. Okay, and this is the shortest path. Okay, अगर K से shortest path जाता है तो फिर that's how it's going to be, that you have a path from I to K which goes through these vertices, and then we have a path from K to J which goes through the same set of vertices, right? Remember, these vertices are not allowed at this point. All right, are we good? So what's the shortest path distance in this case when we actually use the vertex K? I think many of you probably have already guessed. Okay, in this case, this is actually a K minus 1 is matrix के अंदर the distance from I to K plus the same matrix के अंदर the distance from K to J. All right, so we have to go from I to K, and then we have to go from K to J, right? That's it, right? That's it. If there is a path which must go through K, so this must be it, because ये जो I K है, this represents the length of or the weight of the shortest path from I to K, and this represents the shortest path distance from K to J. If there is a path which is of minimum length and it goes through K, तो इसकी value ये होगी. That's it. We have already solved this problem. So हमारा अब जो solution बनता है, let me get a black color here. So हमारा solution is going to be, so AK, where is it? So AK of IJ is minimum of two things, 1 and 2. Okay, and this is 1 and this is 2. Brilliant. That's it. We are done. That's our solution. That's our dynamic programming solution. We are memoizing the distances between pairs of vertices which use a subset of the vertices. And we incrementally increase that subset. उस subset को हम आहिस्ता आहिस्ता बड़ा करते रहते हैं. And when that subset includes all the vertices, we get AN. We actually get the matrix which actually has all pairs shortest path distance.
So can you repeat what you wrote at the end? Kij is equal to min something.
Okay, so basically मैंने थोड़ी सी यहाँ पे ये किया है कि ये 1 मैंने लिखा है, 1 represents this thing and 2 represents this thing. Okay, so this is sort of min of two quantities. One quantity is the first case, जिसमें the shortest path does not go through K. Okay, उस case में this is actually going to be the corresponding entry in the K minus 1 matrix, right? And the second case is when the shortest path actually goes through K. उस case में we computed it to be this thing. Okay, so in दो possibilities में से मेरा जो shortest path होगा वो minimum होगा, right? I try कि does it help me to go through K? Can I find a shorter path by going through K? If it does, though, I'll pick that. If it does not help me, though, I'll actually go through the first K minus 1 vertices. Right? So AKIJ is min of 1, the equation 1 and equation 2, expression 1 and expression 2. Expression 1 is ijth entry in K minus 1 matrix, and expression 2 is the sum of two entries in the same matrix. The first entry is IK, and the second entry is KJ. Are we good, people? Do we have any questions?
I wants to know what the K minus 1 matrix represents.
Let me read it out. Who wants to know what? What was A to the K minus 1? Umair asks. So A to the K minus 1 was the matrix which has the distances between all pairs of vertices, which only use first k minus 1 vertices. Okay, so in the beginning this would be just a0 जो हमारे पास ये वाली matrix थी. From here I would compute a1, right? उस केस में I would just have ij, and then I would have one other vertex, which would be v1. Okay, and then I would compute v2, a2, which would have v1 here and v2 here. Okay, and so on. Okay. Yes, and Song, you are right. So that's probably going to be a theme of dynamic programming, that you at each local step you will have more than one possibilities, and you pick the one which optimizes your function. Okay, इस केस में हमारा जो optimizing function है वो distance है, and we want to minimize it. तो हमारे पास दो solution है जो हमने we can compute them recursively, we can do the dynamic programming on them. And once we have solutions to those two sub-problems, we pick the minimum of them, right?
So where are we memoizing?
We are memoizing here. We are memoizing in this matrix A और जिसका कोई index K है. That's my memo. All right. Let me show you the code. So the thing is, I like this algorithm because of its simplicity. It's extremely simple to describe, and it's extremely simple to write it down. This is the algorithm, and this is the code for this algorithm. So you run so in the beginning, ij is going to be the adjacency matrix, जिसके अंदर जो zeros हैं उसको you have turned them into infinities. Okay, and now you run from k1 to n, and then for each pair I and j, you do this. You update aij with this. Okay, you pick either this quantity or this quantity. Okay, and that's it. यहाँ पे थोड़ा सा एक मेरे ख्याल में जो okay, so so the way I described it, वो ये था कि you are keeping it looks like you are keeping these n matrices. So A0, A1, A2, A3, up till AN. Okay, but the thing is, so once you have AK, you don't need AK minus 1 anymore, right? Because to compute the next entry, you only need the last matrix. Okay, बस लेकिन इस algorithm की जो entry है उसके अंदर they actually don't keep the AK minus 1 either, right? They just use AK. And it works. Okay, but I don't want to confuse you guys. Okay, for now let's assume that you are actually keeping at least two matrices. You have AK minus 1, and using AK minus 1 you compute AK. Okay, but look at this. I mean, look at this code. This is, I mean, 2 loops and 1 line of code, and it gives you the shortest. Of course, initialize करना पड़ेगा आपको aij को by turning the zeros into infinities, but that's about it. Okay, it's a 1 or 2 lines of code, and it gives you the shortest path between every pair of vertices in your graph. And this is actually dynamic programming. We are memoizing A. All right, let's do a quick time complexity of this algorithm. And the time complexity is extremely simple. This is just order n cube, right? Because for every, so this is n and this is n square, okay? And that's it, 3 loops, order n square, order n cube. Are we good? Do we have any questions?
No question, sir.
No questions? Okay, great. I'm gonna wait about 5 more
Essen has
seconds.
a question. Can we do it in lesser time than NQ?
Can we do it in lesser time complexity? So that's actually this is actually quite complex to do it in less than order n cube. It becomes there are algorithms, but techniques for those algorithms are way ahead of what we do in this class. Okay, for our understanding, that's it. That's actually quite. So देखो मैं let me describe couple of things. एक तो ये देखो कि जो आपकी adjacency matrix है, that has n square entries. Okay, there are n vertices, and you want to compare. You want to compute the distance from one vertex, every vertex to every other vertex. तो इसका मतलब ये है कि जो आप आउटपुट करना चाह रहे हैं, राइट, जो आपका आउटपुट होगा, उस आउटपुट का साइज ही ऑर्डर n स्क्वायर है. ओके, n स्क्वायर एंट्रीज उसके अंदर होंगी. इसका मतलब ये है कि कोई भी एल्गोरिदम n स्क्वायर से फास्ट नहीं हो सकता. You can't do anything better than n square. So this is that thing. Okay, so this is sort of one order more than what is minimally possible. But there are certain algorithms which actually do better, not a lot better. Okay, you can't do much better than order n cube, but they require a lot of sort of advanced techniques, which we are not going to learn in this class. But that's it. The DP gives you sort of a simple, easy to write down algorithm which gives you which runs actually pretty fast in practice. Okay, practice में मेरे ख्याल में algorithm that they use to compute RPL shortest path. इससे ज़्यादा practice में fast algorithm नहीं है. All right, anything else? Okay, good. Let's move on. We have one more problem to do.
Ismail has a weird question. Could you please read it?
What?
Scroll down. Ismail has a question.
Where? I don't see it.
Chat में scroll down.
Scroll up. Scroll down, sir. Oh, okay, sorry. So some definitions on the internet consider only bottom-up approach to be DP. Memoization isn't considered DP. Is that correct? No, it's not. DP की मैंने आपको बताया है कि दो properties है. If an algorithm has those two properties, it's a DP. If it contains optimal substructure and it has overlapping subproblems, उसका it's a DP problem. So you have to write a program to a dynamic program to actually solve it. उसको लिखने के दो तरीके हैं. It's a bottom up, which I like. I mean, that's what I always do. And the second part is the top bottom, which is जो हमने लास्ट टाइम किया था कि जो आप रिकर्सिव सॉल्यूशन से उसको सेव करके रख लेते हैं. मैंने दोनों यूज़ किए हैं. दोनों के लिए मैंने एल्गोरिदम डिज़ाइन किए हैं. तो both of them are DPs. Okay, it's a DP. Anything that solves your recursive problem without computing overlapping subproblems again is a DP, as far as I am concerned.